Welcome, Mrs. Mahoney's podcast. This is our fifth and last one for Unit 7, looking at chemical reactions. And today we're going to look at the energy of chemical reactions. So we're at the top of page 18. And if you look at yours doesn't have the word really enthalpy on there. So what you need to do is just make sure you add that word so that you realize enthalpy means the same as heat. Enthalpy, heat, energy. A lot of times we use those words interchangeably. Heat, energy, enthalpy. So just make sure that if you ever see this word, what is the enthalpy of the reaction? We're talking about the heat. And so then if we look at our abbreviation, we call the enthalpy is H, not E. E is entropy, which we will get to next year. For you that decide to take an AP Chem, we'll talk more about entropy. But enthalpy is looking at the heat of the reaction. So again, here's that triangle H. What does that triangle mean again? Just like in temperature, remember triangle. The triangle means change. And that's what we're looking at now. What is the change of the energy in that reaction? So this is what you can write down. The whole formula. The difference between the sum of the enthalpies or heat of the products and the sum of the enthalpies of the reactants. That's it in words. Okay, what is it in a formula? Okay, this, again, when we borrow from the Greek, this stands for sum. So this is just this whole thing in a formula, change in enthalpy equals the sum of the products minus the sum of the reactants. Okay, now what you guys are really going to be seeing is, because we're not going to be summing up the products and the reactants, let's just get rid of it and just realize what do you need to do. It's the heat of the products minus the heat of the reactants. The order matters. It has to be products minus reactants, because that's going to tell us if it's exothermic or endothermic, whether this comes out to be a positive or a negative. So again, in simple words, what this means is the energy of the products minus the energy of the reactants determines the total energy of the system. Yes, you need to know this. This is something that you definitely need to know. How do I calculate delta H? Take your heat of your products minus your heat of the reactants. Okay, so we're going to start looking at a lot of graphs. So what we need to do is make sure we can understand these graphs. This one didn't print very well, but you have one written yourself there. Okay, this is always your reactants. So make sure on your labeling, I would highlight it or you could see it. This stands for reactants. Okay, your products are on the right, just like when you write an energy, or excuse me, write a reaction, and we know that we have reactants on the left side becoming products. We read the graph also left to right. In the forward reaction, you have reactants becoming products. Reactants becoming products. Now when I see this, it tells me a story. What's happening is I'm adding energy, So look, you have to climb this hill. That right here at the top, this is called, and I would add this to your label, this is called the activated complex. And what that is kind of a little mutant. And what it is, it's not really reactants and it's not really products, because these bonds have broken and they're starting to form the new products. So at this point, it's not really a reactant or a product, but we have enough energy to now start making the products. So when we climb the hill, going up, breaking bonds from the reactants to the top of the hill up to this activated complex, this is endothermic. It takes energy to break bonds. Then once you've reached that, now we're going to start making our products. So bonds are being formed. When bonds are formed, energy is released. That is exothermic. So the difference between this determines if it's an overall reaction is endothermic or exothermic. Okay, so right here, this energy, the energy to climb the hill, to get the energy, to get the reaction activated. What does activated mean? Started. So this is called the activation energy, the minimum amount of energy needed to start that reaction. Hopefully that should make sense. How much energy to activate the energy. So if you don't have enough energy to get this reaction started, if you don't have enough of this activation energy, the reaction will not go. Okay, well, you can add a catalyst to lower this activation energy. And that's what a catalyst does, is when you add a catalyst, so notice the red line here is what it really should be without the catalyst. And we're just using an enzyme. Look at your biology. This is where you've heard of a catalyst. So what happens is you throw in a catalyst. Look at it, doesn't change my reactants or my products. All it does is lower the amount of activation energy, so lowers the amount of energy to get it started. Therefore, the reaction will go faster because it's not going to take as much energy to get it going. So that is what a catalyst does, lowers the amount of activation energy so it's easier to get that reaction started. Okay, you have some graphs, and a lot of it's labeled on your graphs, but I just want to make sure you have all this information, and let's just kind of add what this graph can tell you, because actually in a graph, you should get to where it can tell you a lot of information. So this first one you're looking at is an exothermic graph. How do I know that? When I'm just looking at a graph, I can tell right away if it's exothermic or endothermic. Compare the products to the reactants. If the products are lower, at the lower energy than the reactants, this is showing you a graph of an exothermic. And again, I'm talking about in the forward reaction, reading it left to right. That's called the forward reaction. So what happens is exothermic's releasing heat to the surroundings. So look at it's going to release more heat than it took to break those bonds. So when you subtract this, products minus reactants, that's going to give you a negative number. And if it's a negative number, that's another way I can tell that it's an exothermic. So exothermics have if the delta H is negative, that's how I can tell it's exothermic. These are the ones they feel hot. You had it, you threw magnesium in with your hydrochloric acid. I wanted you to feel that test tube so you could feel that it was actually getting hot. That's exothermic. It's releasing the heat. This is what you're feeling, is this heat given off to the surroundings. So you feel it as hot because it's releasing the extra heat. This is definitely, if there's that question I said on the test before, we weren't ready to answer it, this now would be ready to answer it, because it asked, in an exothermic reaction, how does the heat of the reactants compare to the heat of the products? Now we can kind of see that. Well, the products are less than the reactants because it's given off heat. So that was why I was kind of upset that we had that question on there. We weren't ready to talk about it. After this, then yes, I'd feel like it was a fair question. Does that mean it could show back up again? Something similar to it? I wouldn't be surprised. Okay, now again, I would label here, this is called the activated complex, because sometimes I might ask you, where is the energy of the activated complex? That's the top of the hill. That's the very top of the hill. Okay, let's compare it then to our other graph. Notice the difference when I'm just looking at it. The reactants is the same, products is the same. Activation energy, energy to reach the top of the hill. This is still the activated complex. So the labeling of it doesn't change. Oh, also, notice right here, it was on the other one, I just didn't point it out. Remember, what is that delta H? The difference between products and reactants. So if I look at this one, when I subtract this time, it's going to give me a positive value. So when I just look at it, and if I'm given a value and it gives me a positive heat, I know it's endothermic. It gives me a negative heat, it's exothermic. So again, this one took more energy to break those bonds than it released. These are the ones that are going to feel cold. And they feel cold, and this is the one that's kind of sometimes seems a little weird, because it's like, well, it's absorbing energy. If it's absorbing energy, shouldn't it feel hot? No, the system is absorbing energy, but it's stealing it from its surroundings. So its surroundings feels colder because the system has taken the heat, leaving less heat in the surroundings. That's why you feel it being cold, because you're actually seeing the absence of that energy, because the system took in that energy. So again, in the forward reaction, that's when you're going to see it going to be a positive, and it's because products are greater than the reactants. Okay, just find a little place to kind of write down some notes. You don't have to copy this word for word. What you just need to realize, reverse reactions can happen, and it could ask you about a graph, or I could ask you about a graph in the reverse. That just means read it backwards. Products become reactants. Reactants would become the products. And so just know that everything would be backwards, reverse. So in the forward, if it's exothermic, the reverse would be endothermic, and vice versa. If the forward is endothermic, the reverse has to be exothermic. This is an example. I know that it's endothermic to decompose it, but in the reverse, it's going to be exothermic. So if I look back at this, well, if you just read this backwards, this is how you can see the graph all of a sudden becomes exothermic, because now this would become, in the reverse, this would become my reactants in the reverse, and this would become my products. So you could see in the reverse, products would be lower than the reactants. That's why it's exothermic in the reverse. Okay, so let's just kind of practice. This is where you don't have to write anything down. If you had this graph, purely, is this an endothermic or an exothermic reaction? Yell out the answer. Make your parents, make people wonder, especially if you're watching this on a phone somewhere randomly, that you're just saying out these random answers. Okay, hopefully looking at this, this is exothermic. How do I know? Because the products they are giving off, the products are lower, less than the reactants. This is an exothermic graph. Waiting, waiting. Endothermic. Products are greater than the reactants. So from this, and again, it tells us a lot of information, but quickly, just by looking at the graph, you need to start recognizing the difference between the two. Yes, you're going to see this on that test on Friday. Yes, you can see this definitely on those CAs. You need to recognize the graph. Okay, also from the graph then, we can start then pulling out more information. So this is on page 19, and you're just going to start then pulling actual numbers from this, but you need to know what it is. So if you need to label it, I would label it. What is this? These are my reactants. What else do I know? These are my products. Okay, so I'm going to start going through. The heat content of the reactants are the forward reaction. Okay, where are the reactants is what this is asking. And it's right here. Your answer, 80 kilojoules. Okay, don't forget to label. I've been nice and label these for you. If I don't have a label, look at your graph. What do I label it? I label it kilojoules. You could abbreviate that, kJ, kilojoules. Okay, number two, the heat content of the products is about, where's the products? I'd say it's 160. Okay, the heat complex of the activated complex. It's where you have to know, again, this is where you know where the graph is. Where's that activated complex? That's the top of the hill. So what is that energy at? That's about 240 kilojoules. Okay, now, this is where simple math comes. The activation energy in the forward reaction. Okay, activation energy from the reactants to climb the hill. How much energy did it take to climb the hill? So we were at 80. How much to climb up to 240? So how much is 240 minus 80? Mental math, 160 kilojoules. So that's how much energy. You could either subtract it. You don't like subtracting? Okay, fine. You kind of add. You just go, okay, there's 40, there's 80, there's 120, there's 160. You could subtract, you can count it to get that 160. Seriously, no calculators needed. Okay, heat of reaction in the forward reaction. Okay, what was my heat of reaction again? That's this. Remember, heat of reaction is the difference between your products minus reactants. So products are at 160, reactants are at 80, so 160 minus 80, so 160 minus 80, so the heat is 80 kilojoules. So in the forward then, this reaction is endothermic. Two ways. You can look and you see the products are higher, or right here, this is a positive value. Positive value means it is am endothermic. Okay, let's look at the next questions then. The heat, okay, now we're going to look at everything in the reverse. So in the reverse, all of a sudden these became my reactants. These became my products. So in the reverse reaction, the reactants then now are sitting at 160 kilojoules. The products in the reverse then are at 80 kilojoules. The heat at the activated complex, that doesn't change. Look at your reverse. The hill, the top of the hill doesn't change. So it is still at 240 kilojoules. But what does change, look at your activation energy. It's still from the reactants to the top of the hill. So from the reactants to the top of the hill, how much did it take this time? It took only 80 kilojoules to get the reaction going in the reverse. Okay, the heat of the reaction, this is just a weird font change, that should be a delta H. Okay, now again, this time remember, delta H is still this distance, but what has changed? If we write it, products minus the reactants. Okay, products minus reactants, so now it's a negative 80 kilojoules. The value is the same when you reverse the reaction. It's the sign that changed, only the signs. So this means then in the reverse reaction, you're going to see an exothermic. They're opposite each other. Okay, so tomorrow we'll finish kind of using your own graphs, and then if I give you numbers, you can draw your own graphs and start kind of wrapping up this whole chapter to get ready for the test we have on Friday. See you tomorrow.